While we get the DocCam thing to work, I'm going to try to stay as much on the computer as possible, but I might have to switch to the whiteboard and back.
Okay.
Would that be like too much trouble for you guys?
You're fine.
Okay. Okay. Thank you. All right, guys. So it's officially time. So let's get started. Hopefully, we get DocCam soon. But if not, I mean, you're still going to get a review. So it's weird that I'm facing you level. A joke to start. So a photon checks into a hotel room, and the receptionist asks, "Do you need any help with your baggage?" And the photon responds, "No, I'm traveling light." So, anyways. All right. All right, as you know, like this might not include all the material that you might have to know for the final. It touches on the majority of subjects, so I think it's a good review, but still complement it with your slides and your quizzes and tests from the semester and your textbook. And there's a chance it might include errors, so just double check everything. If you have any questions, if you see anything, let me know. And we'll address it. All right. Oh, okay. Yeah, go ahead. Brief intermission.
Sorry.
It's okay.
Turn the laptop around and face the students, you can do that too. It's up to you.
Yeah, it's just a little weird to be facing them back.
You can flip that around.
Okay. Should I wait until they're done?
Yeah. Unless there's one.
Okay, thank you. Should I continue?
Yeah, you can go.
Okay. All right. Sorry again. Okay. Whoa. All right.
Sorry.
No, it's okay. No worries. All right, I think this is better. I like seeing you guys. Okay. So, while we work on that. So I started like in the order how we covered. Oh, that's not very smart because you guys can't see. Oh God. All right. Is that better? Okay. So I did the review in the way you guys covered the content of the material throughout the semester. So it starts with 7, 8, 9, 10, and then it goes back to 5, just like you did for Chem 1B, like your class. Like these are like the main equations I found for the chapter. So remember, energy is equal to h times nu. So energy is equal to Planck's constant times the frequency, and the frequency is equal to the speed of light over the wavelength. Those two, make sure you know. Then we have this one for other calculations. Most of the time this one's given. Here's your Planck's constant that will be given, your R given, and your C, speed of light, also given. I believe you have to know this one. I'm not sure. Boyle, it's equal to the wavelength. It's the wavelength. It's equal to h, which is the Planck's constant divided by. Yeah, sure. All right. Okay. Hello. Hello? Okay. Better? Okay. Thank you. All right. So the Boyle's equation, the wavelength is equal to the Planck's constant over the mass in kilograms times the velocity in meters per second. All right. So make sure you're familiarized with that, this diagram, and you know you're able to compare frequency, wavelength, and energy. In this case, you see radio waves here, and those are the ones with the longest wavelength, and that means they're the ones with the lowest energy. Remember that energy is inversely proportional to the wavelength, and inversely, so radio waves are the longest wavelength and the lowest energy, whereas towards this side, where you have the gamma rays, you have the highest frequency, highest energy, so shortest wavelength. Does that make sense? Yeah, okay. So frequency is the number of waves that pass a point during a certain period of time. And so, like I said, greater wavelength equals smaller frequency.
We're going to come over here and try it.
Okay. Yeah, go ahead.
Which one would it, the A?
Yeah, it's okay. All right. So a way to remember like the orientation of the visible light, you can remember as Roy G. Vib. So red, orange, yellow, green, blue, indigo, and violet, in that order. You guys have any questions? No? All right. Ugh. All right. So it says an energy of 2.0 times 10 to the 2 kilojoules mole per mole is required to cause a cesium atom on a metal surface to lose an electron. Calculate the longest possible wavelength of light in nanometers that can ionize a cesium atom. So I think I'm going to go ahead and like solve that on the whiteboard. I'm going to write as big as possible so everyone can see it. That's okay. Everyone has copies, right? Or access to this? Okay. All right, so we know that our equation is energy equals Planck's constant times the frequency, and we know that this, we can plug it in as C over wavelength, right? So they gave us that the energy is 2.0 times 10 to the 2 kilojoules per mole. The thing is that the energy here in this equation is joules per atom, so we need to do some conversions using Avogadro's and what we know for kilojoules versus joules. So multiply this. So we know that 1 kilojoule is equal to 1,000 joules. To convert it to joules. And then we know that 1 mole is equal to 6.22 times 10 to the 23 atoms. So when I multiply that, it gave me that energy was equal to 3.32 times 10 to the negative 19 joules per atom. Does that make sense so far?
Shouldn't that be switched because it's kilojoules per 1 mole so that the moles are on top and the atoms are on the bottom?
Wait, what?
So you see at the beginning of kilojoules per mole.
Right.
So it's 2 times 10 to the 2 over 1 mole.
Oh, yeah, you're right. Sorry. Yes. Thank you. Let me switch it. All right. Good catch. All right. And so now that we have that, they're asking us for wavelength, so we can just go ahead and plug it in. So let me not rewrite the equation. So 3.32 times 10 to the negative 19 joules per atom is equal to Planck's constant and then the speed of light, 8 times 10 to 8 meters per second over the wavelength, which is what we're looking for. So we have to rearrange that. So our wavelength will be equal to the 6.626 times 10 to the negative 34 joules per second times 2998 10.8 meters per second over the 3.32 for the energy. So when I saw that, I got 6.0 times 10 to the negative 7 meters. And usually our wavelength is given in nanometers, so be careful with that once you start a problem with the wavelength given, because most of the time they give it in nanometers. So remember to convert it to meters so it can cancel out. So this is equal to 600 nanometers. Does that make sense? Yeah. Yeah. Can you see? Can everyone see? Yeah? Okay. All right. Everyone good with this? So it seems like I'm gonna stay with the whiteboard. I'm gonna try to move as quickly as possible. So if you guys have a good understanding of something, just let me know and then I'll go quicker to save time. Is that okay with you guys? Yeah, okay. I have some copies of the handouts you were given while we were looking at this. So I have the one that has the energy levels. I don't know if you remember. So you can take pictures of all those handouts when we are done. Yeah? All right. Can I erase? All right. So next on the list is quantum numbers. Sorry. So remember we have 4 quantum numbers, right? Our main one is the n, which tells us the energy level we're dealing with. And this is equivalent to the period in the periodic table. Period in so period or row. So as n increases, the size, energy, and electron capacity all of a sudden increases. Like you can fit more electrons as your n level goes up. Does that make sense? Then we have L, which is, so each one of the quantum numbers depends on the previous one. So our L, the way we find it is n minus 1, and that tells us the shape of the orbital we're dealing with. And so you know that if L is 0, that corresponds to an s orbital. If L equals to 1, that's a p orbital, 2, a d orbital, and 3, a f orbital. Does that make sense? It's ready? Okay, great. All right, we're switching over, guys. Thank you. Sorry. Oh. So let me show you the handout I was talking about. Okay. All right. You guys remember this? So remember, if you're moving up, your electron or photon is absorbing energy. If it's going down, it's decaying, so it's emitting energy. And something very important here that I saw, let me focus it. Oh, I don't know if you can see, well, you can see the bottom one. So this one represents the highest energy transition, because you see the space between the energy level 1 and energy level 2 is the greatest. So it corresponds to the highest energy, highest frequency, and shortest wavelength. Instead, we have this top one that corresponds to, it's the shortest transition, so it's the one with the lowest energy, lowest frequency, but longest wavelength. That's what I wanted to show you there. Does that make sense? So be able to recognize them from diagrams like that. Okay. So to continue with the quantum numbers, so we said this is the energy level. Oof. Oh God. Can you? Oh my gosh. Okay. Energy. So I'm gonna have to write in pen. Energy level. L is n minus 1. If L equals 0, that's S. 1 is P. 2 is D, and 3 is F. And then our ML depends on the L value. So remember, it's negative L going through 0, and then going through plus L. I don't know why it looks like this, guys. There we go. Okay. And then finally we have MS, which equals our spin. So the two possible values are plus 1/2 and minus 1/2, where the one looking up is the plus 1/2 and the one looking down is the negative 1/2. Does that make sense? Oh, should I use the microphone? Okay. Hello? Okay. All right. So I included the table from class here, just so that you're familiar with it. And like, don't try to memorize this table. Try to understand why. Do a couple of practice problems. I mean, I included some here on this, but the idea of it is so that you can understand how to work this out. So for example, we don't start seeing F orbitals until energy level 4, because remember our L value depends on n minus 1, so 4 minus 1 is 3. That's when we start seeing the f orbital. And remember we have only one s orbital, so our maximum is 2 electrons. We have 3p orbitals, so we have a maximum of 6 electrons, and that's because we can only fit 2 electrons in each orbital. So 2 times 3 is 6 electrons. We have 5d orbitals, and we can fit 2 electrons in each, so that's 10 electrons, and then 7 f orbitals, 2 in each, that's 14 electrons. So know the maximum number allowed. These are easy to spot. Oh, and if you want to find out the number of orbitals, you can always do n to the square power, and it'll tell you the number of orbitals. Okay, so to practice, which of the following represents valid sets of quantum numbers for a set that is invalid? Explain briefly why it is invalid. So first we have n equals 3, L equals 2, ML equals -3. So this one is invalid because we're fine from n equals 3 and L equals 2, but our ML cannot be greater than or less than -2 or +2, because that L equals 2 is limiting us in terms of the value of ML we can have. So this is invalid. Okay, so up to 2. All right, the second one. So n equals 2, L equals 1, ML equals +1. That one's valid. All of them fall within the range. For our third one, so n equals n equals 6, L equals 5, ML equals -3. That one's valid. So remember, your ML values are possible ones, like all the ones you can possibly have, but it doesn't necessarily have to be like -5 or +5. So this is valid. And for the last one, n equals 4, L equals 4. So that one's invalid because the maximum value of L is 3. All right, can I move on? Yeah, okay. And then you can come take pictures at the end if you need them. All right. Okay, so I just wanted to include this picture so you guys know how many orbitals we have. So you can see 2 electrons in each. For a D, we can fit 10 electrons. So 1s, 3p, 5d, and 7f orbitals. So now we get into orbital filling and the rules of doing that. To do that, electrons occupy the lowest energy orbital available. So that goes with the rules. And then they fill up in a specific order. So you can either do it by the periodic table or by like the upside down rain method. I'm gonna go ahead and do the one using the periodic table. So you know that these first two corresponds to the S block. S block. This middle one corresponding to the transition metals. It's corresponding to the D block, P, and then this bottom one is the F block. Yeah. So you will go by how the periodic table is set up. So 1s, 2, 2s2, 2p6 here, 3s2, 3p6, and so on. So the row determines the number in front of your orbital, and then depending on the block you're in, you're using S or P or D. You can either write it longhand, which is going through all that, or you can write it shorthand. So I'll go ahead and write lithium both ways. So for lithium, it's number 3. And so longhand would be 1s2, 2s1, right? So 2 maximum in the s orbital, and then we have an empty one here. That's a long way. The short way is putting into brackets the noble gas prior to that element and just filling up the rest. So in this case, in the case for lithium, we have He, because that's the noble gas prior to that one, and then the 2s1. So this tells us, too, that the lithium has a valence electron of 1. I think we go more into detail in a little bit, but okay. So remember your rules. Pauli exclusion principle, no 2 electrons in an atom can have the same 4 quantum numbers. Your Hund's rule, when filling degenerate orbitals, electrons fill them singly first with parallel spins. So if you have a 3p and you have 4 electrons, you have to first fill each one unpaired and then start pairing them. You wouldn't be able to do it 2 here and 2 here, because that would be against Hund's rule. And off-ball, the off-ball principle says that you fill up the lower energy levels first. All of them are very important. One example I wanted to give you guys for Pauli, if we have a 1s orbital and it's completely filled, so those 2, right? Their n value is 1, their L value is 0, their ML can only be 0. So far they have the same 3 quantum numbers. So what differentiates them is their MS value, because one of them has a positive 1/2, and then the other one has a negative 1/2 value. So that complies with the rule that you can't have the same 4 quantum numbers. Any questions? Like this? There? Got it? Yeah? All right, good. Okay, so valence electrons, you should be able to distinguish valence electrons from core electrons. Remember that for our main group elements is, for example, for our S block, it will be ns to the power 1 or 2. For our P block, would be the ones from the S orbital, so ns, plus the ones in the P orbital, so ns2 and then np with the possibility of 1 through 6. Instead, for our transition elements, remember we have the ns ones and then n minus 1d. So they're 1 row behind. Let me write that here. So remember, valence electrons are electrons in shell. Shell only has 2 L's, okay, with highest energy level, so the outermost electrons. So those are the ones that typically participate in the chemical reactions. And so for our main group elements are NS and NP. Whereas for our transition metals, we have NS and N minus 1D. The F block, they're 2 rows behind, but we usually don't get that far. I would just be familiar maybe with that. We typically stay in the first couple of elements. All right, so it says determine the number of valence electrons in each element. So our barium atom is on the second column. So that means it's going to have 2 valence electrons. Our cesium atom is on the first row, so that means 1 valence electron. Our nickel is one of the transition elements. So remember, we're going to have 2 here, and then 1, 2, 3, 4, 5, 6, 7, 8. Oh, hold on. 2. Okay, yes, so it's 10. So it's 2 from the S and 8 from the D orbital, so 10. I don't know, I miscounted the first time. And then our sulfur is on the P block side, so we're going to have the first 2, 2, 3, 4, 5, 6. Does that make sense? Yeah? Okay, good. All right. Oh, I already worked on the electron configuration, and they solved the same one. So writing all energy levels that are filled with electrons and how many in each, shorthand using the nearest noble gas preceding the element in question to shorten the electron configuration. So there's more practice here, so let's go ahead and do that. So they're asking for the electron configuration for selenium, and it's the longhand one. So selenium, it's on the fourth row on the P block. So we're going to have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Remember that once we reach the d orbital, we're 1 behind of the main one. And then 4p, 1, 2, 3, 4, 4p4. If we were to write it shorthand, we can just do argon 4s2, 3d10, 4p4. I was going to tell you guys something and I forgot. All right. Oh, you can always double check by adding up the exponents, and you should be able to get the same number corresponding to that atom. So in this case, selenium is number 34, so all these should add up to 34. And the right answer for this is B. All right. Does that make sense with everyone? Okay. Yeah. Okay. Oh, God. All right. All right, so what is the electron configuration for one of the ions for iron, and indicate whether it's paramagnetic or diamagnetic. I know it may seem tempting to go ahead and write the main configuration for that ion, but I always suggest writing the neutral one first so you don't make any mistakes. In this case, we can do the shorthand. So for iron, it's argon, 4s2, 3d, 1, 2, 3, 4, 5, 6, 3d6. And so they're telling us to write the one for the 2+ ion. Remember, you have to remember this. In the transition elements, we fill the s orbital first, and that means that when we remove electrons, we remove from the s orbital first as well. So you're actually going to take those 2 electrons from the 4s orbital, not from the 3d. So be careful with that. You may see this written as 4s to the 0 power, which is equal to 1, 3d6, or you may just see it as that. In this case, I think they put to the 0, yes. So the correct answer is C. Does that make sense? So remember to always remove from the s orbital first when you're dealing with transition elements, because a lot of students miss this type of questions. Sorry. All right. So periodic trends. Once again, this is something I suggest understanding rather than memorizing, because there's plenty of them, and so I don't want you guys to like be forgetting about them in the middle of the test. So aim to understand them. So I'm going to start with the atomic radius. So you know that your atomic radius increases going down, and that makes sense, right? Because we're increasing, we're adding energy levels, we're adding those end levels, end values. So our capacity to carry electrons increases. So that makes our atomic radius bigger. So it increases going down. So let me write it. Radius. Bottom. And decreases left to right because of that C effective. So the effective nuclear charge makes our atomic radius decrease from left to right. Remember that the effective nuclear charge is the strength of the nuclear charge that the outermost electrons are feeling. So that's related to atomic radius. Let me see. So I'll do ionization energy next. So our ionization energy increases from left to right, and if you think about it, that makes sense because this side of the periodic table includes our non-metals. So if you think about the definition for ionization energy, which means the energy associated with removing electrons from an element, those nonmetals are going to want to hold on to those electrons instead of like giving them away. So your ionization energy should increase from left to right because of that. That goes along with electron affinity as well, because those nonmetals are going to be more willing to take those electrons. So they're going to be like, it's going to be easier to add an electron to them. It's going to be more exothermic going that way. And so let me add IE. Associated. All right, and then metallic character, well, you know that towards this side of the periodic table we have the metals, so it makes sense that metallic character increases going that way, towards the metals. And the one that's missing here is electronegativity, so remember that electronegativity increases going that way, and that also makes sense because it's a non-metal, so the pool for those electrons. If you forget the trend for electronegativity, just remember that fluorine is the most electronegative atom, and that should help you remember. Electronegative atom. All right, so we get into, oh, I forgot to cover ions. So let's go into the ions for a bit. So we have cations, and we have anions. So cats are positive, onions are negative, anions, I don't know, that helps you remember. So remember that cations lose electrons and anions gain electrons. So in the case of cations, they're going to be smaller than their parents. And a way to remember that is maybe if you're carrying a bunch of bags in your arms and they're very heavy and you have a lot of them, if you lose one, then you have greater control, greater pull to your center for those bags. So you like decrease your arm length. I don't know if that helps you. And then anions, they're going to be larger than their parents. And this is because we're adding more electrons, so those electrons are repelling each other, and so they're making that circumference bigger. So in this case, to order them in order of increasing radius, we have cesium, xenon, and iodine. So here, here, here. And following what I just told you guys, you know that the cesium, since it's the cation, it's going to be the smallest one. Then we're going to have our neutral, xenon, and then our iodine atom. It's going to be the largest one. And then this brings up a very important concept, and it's the topic of isoelectronic. So these three elements are isoelectronic, meaning they have the same number of electrons, and what differs for them, for each one of them, is the number of protons. So cesium is going to be the smallest, since we have protons, more protons pulling those electrons. The answer is B. All right. Okay. So this is a more conceptual question. So it says the ionization energies of an unknown third period element are shown below. Identify the element. So the way we identify these elements are by seeing the trend and seeing where we have the greatest jump in energy. So we see that our first to second increases normally, our second to third increases normally, our third to fourth increases normally, but then when we get from fourth to fifth, we see that huge jump from 4,360 to 16,100. So that jump corresponds to us trying to remove a core electron, which requires a lot of energy. You know, outer electrons are easier to remove than core electrons. So this, let me show you how I do this one. So, well, I'll tell you the answer and then I'll explain it. All right, so this is silicon. And that makes sense because our first ionization energy to remove that first electron is normal. To remove one from here is normal to here. To remove the following one is normal. And then the subsequent one is normal. But then that has a full shell. When we're about to remove that next electron, that's when we get into that huge jump of energy from fourth to fifth. All right. So for which element is the gaining of an electron the most exothermic? So the easiest one, the most viable one, the one that wants that electron the most. And if you take a look at here, you see that fluorine is one of your options. So there we go. That one was easy, right? It's the most electronegative atom. If you want me to draw it. More exothermic. All right. Choose the larger atom from each pair. So between aluminum and indium, so they're in the same group. So indium is going to be larger. Silicon and nitrogen. Silicon and nitrogen, so silicon is going to be larger since it's one row below. Phosphorus and lead. Phosphorus and then Pb. Pb is all the way down here, so Pb is going to be larger. And then carbon and fluoride. So carbon is going to be larger than fluoride. So this is the same concept and the same question we got into, for this one. So I'm just going to give you the answer so we can move faster through the guide. Question? No? All right. Okay, so where we know that our magnesium ion is going to be the smallest one and our oxygen ion is going to be the largest one. If we were to draw the full diagram orbital for each element, we would see, so for nitrogen, I like to write the normal configuration first and then doing the orbital diagram. So I'm going to do the short one. So helium, and then 2s, 2p. So we have 1, 2, 1, 2, 3. Okay. Fluorine, we have same He, 2s. So we have 5. Magnesium, neon, and then aluminum. We have neon again. Oh, sorry. For magnesium is 3 because we're on the third row, not 2. And for aluminum is 3s completely filled, and then our 3p, only one of them. All right. Okay. So, any questions? No? Okay. So which pair of elements is most likely to form an ionic bond? You know that ionic is metal plus non-metal. So out of those, it will be calcium and oxygen, since calcium is a metal and oxygen is a non-metal. All right, for 11, your guide says decreasing, it should be increasing. I don't know if you guys see that. Bless you. Increasing. Okay, so we're dealing with oxygen, sulfur, As, and Ge. So if we see them on the periodic table, oxygen, sulfur, As, and Ge. So it will be increasing that way, right? So increasing electronegativity to oxygen. So your answer would be B on the other side. So being oxygen, the one with the highest electronegativity, and I think this is germanium, I'm not sure, the lowest electronegativity. All right, we get into ionic bonding and covalent bonding, and this is going to help you remember for your naming. Remember, it's different for ionic and for covalent, for binary compounds, so that's something that helped me remember. It's the difference between them. So ionic bonding is, as we know, metal plus non-metal, and it involves the transfer of electrons. It's not sharing. The way I remember is I don't like to share, so it's transfer and not sharing. Ionic bonding occurs between a metal and non-metal. high melting and boiling points, high polarity, solid at room temperature, and then we have lattice energy and Bohr-Haber cycle. Some examples include sodium chloride and magnesium chloride. And then covalent is the sharing of those electrons. Occurs between two or more nonmetals. We have low melting and boiling points, low polarity. Some examples include CH4 and N2. All right, so I wanted to go into lattice energy. Since it's a topic I saw like it's very emphasized in class. So remember that our energy is equal to the charge of the cation. So I'm just going to put, to save space, I should have moved it, times the charge of the anion, over the distance. And so remember that lattice energy will always be negative. And it says lattice energy becomes less exothermic as ionic radius increases, and lattice energy becomes more exothermic as magnitude of ionic charge increases. If you see the formula, you see that, so the energy is equal to the product of the charge of the cation times the charge of the anion over the distance. So if the distance between our ions increases, then our energy decreases. Whereas, and then if the charges, if the product of the charges increases, then our energy increases. Just look at where they fall on the equation. So if something is on the top, then it's directly proportional to this. The distance is inversely proportional to energy, lattice energy. I brought the handout from class too. Just take all this. Okay. So here we go. I think this was a good summary of all your lattice energy information. So they were telling you to organize all these ions, all these compounds into increasing lattice energy. So we know that the ones with highest lattice energy are going to be the ones that result in the biggest product. So 4, and I think we have 6, maybe not. Oh, here we do. So 6, -4, -2, -1. And then for ionic radii, we know that the ones with like -2 are going to be larger than the ones with like -1 per se. So the way they arrange this is lowest KCl, highest Al2O3. So KCl, the product is -1, whereas this one is -6. And they just like arrange all those around that. Does that make sense? So first take into account the product of the charges, and then if you're dealing with the same charge, then consider the radii and how that may impact your answer. I think that's going to save you time. Yeah, okay. We can come back to that if you guys have more questions at the end. All right. For Lewis structures, so know your steps. I think if you know your steps, if you happen to get stuck and you remember them, then it's going to be easier to solve the structures. And this is a key point for Chem 1B, since a lot of things fall into that: polarity, hybridization, electronic geometry, molecular geometry, and so on. So steps. Number 1, count valence electrons. 2, determine the central atom. Usually it's the one that needs the most electrons to fulfill its octet. 3, distribute the bonds between the atoms, then add lone pairs to terminal atoms. And 4, if there are any remaining electrons after terminal atoms have their octet, go to the central atom. So only use double and triple bonds when you need them. So leave that as the last resource. I think we have time to do some structures. Okay. So I picked 3 from the table you're going to get. Remember that you have to know the angles, and it won't include the examples or the hybridization. So I just took 3 out of this and solved them to review with you guys. So I chose BF3. So if we count the valence electrons, so remember that for this is valence electrons. Remember that when we get to molecular orbital theory, it's total number of electrons. So don't get those confused. So boron has 3 valence electrons, and fluorine has 7, and we have 3 of them. So when added, that is equal to 24. So the way I see this, we have 3 fluorine, so boron has to be our center atom. Let me do it a little, yeah. Okay, and so we subtract the electrons from the bonds. 2, 4, 6, so 26 minus 6 leaves us with, can't do math, 18, right? Okay, thank you guys. All right, and then we proceed to fill out the outer atoms. 2, 4, 6, 2, 4, 6, to give everyone an octet. 2, 4, 6. All right, and so 6 times 3 is 18, so we used up all our electrons. So I like to keep tally of the electrons I've used. I think that keeps things organized, and most likely it'll help you get the right structure on the first try. You might say everyone has an octet but boron. Remember that boron is one of our exceptions. So remember your exceptions for less than 8 valence electrons include hydrogen, which only needs 2 electrons. Beryllium, which needs 4 electrons to fill their outermost shell, and aluminum / boron, they're on the same group. They only need 6. So those are for reduced octets. For expanded octets, remember we have any element on row 3 or below can have expanded octets. All right. So when you check your table for electronic geometry, that will be equal to trigonal planar, and then that's the same molecular geometry since we don't have lone pairs. So electron geometry, trigonal planar, molecular geometry, trigonal planar too. And then the angle is 120, so remember that. All right, any questions? No? We're good? Okay. The next one I chose was an ion. So IF4, like molecule with a plus charge. So both of them are halogens. So they have 7 valence electrons. So 7 plus 4 times 7, minus 1, remember that that plus means it lost an electron, so that's equal to 34 electrons. And like I told you guys, we have 4 fluorines, so the one in the middle is going to be iodine. So I, F, 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 F. All right, so far we've used 2, 4, 6, 8. So that gives us 26 electrons. So let's fill out the outer atoms. So in that we used 24 electrons. So we have 2 electrons left, and so they go on the center atom. So 2, 4, 6, 8, 10. So iodine is on row 5, I believe. Yes, 5, so it can exceed the octet. Remember that for ions, you need to put the brackets to indicate that they've lost or gained an electron and the plus sign outside. I don't know what I did with the, okay, there we go. And checking at your handout, your table, you're going to see that it's going to have an electronic geometry of trigonal bipyramidal, but a molecular geometry of seesaw or distorted tetrahedron. So and then molecular geometry of seesaw. So remember that what changes is your molecular geometry. Your electronic geometry never changes despite if you have lone electrons, lone pairs of electrons or not. So remember that. Okay, and then the last one I chose, just because it's very used. All right. Was our carbon an ion? So we know that carbon has 4 valence electrons, oxygen has 6 valence electrons, and we have 3 of them. And we've added 2 electrons. So that gives us a total of 24 electrons. So again, carbon, the middle, oxygen, oxygen, oxygen. Okay, so 2, 4, 6. That leaves us with 18. 2, 4, 6, 2, 4, 6, 2, 4, 6. Okay. 0. And then you might think, okay, I'm done because we've used all our electrons, but realize that carbon doesn't have a complete octet, and carbon is not one of our exceptions, so we need a double bond. So make that into a double bond. Now carbon has 2, 4, 6, 8 electrons. And remember, when there's double bond, there's a possibility for resonance. I don't know where it's at, but -2. Okay, so charge -2. So the resonance structures for carbonate, you just rotate that double bond. And looking at your chart, it has a trigonal planar electron and molecular geometry. And angle is 120. Oh, and I don't think I gave you the angle for IF4. So it's supposed to be 120 and then 90, but remember that the lone pairs of electrons make that angle smaller. All right. Okay. So getting into bond lengths. Forgot where I was going with this. Okay. So bond lengths, distance between the nuclei of bonded atoms. So we know that our single bond is going to be longer than a double bond and a triple bond. So we say that length and strength are inversely proportional because their triple bond is going to hold those nuclei closer together. So to the strength. So single increasing length and then increasing strength should be single, double, triple. So the same, but with the little signs inverted. Okay. Remember that a single bond contains one sigma, so, and then a double bond is a sigma bond and a pi bond, so one of each. And a triple bond is a sigma bond and 2 pi. Oh, I hadn't realized that this was like written here. Length and strength are inversely proportional relationships. The shorter the length, the stronger the bond. One thing I wanted to remind you guys, sigma bonds are made from head-on overlap. Pi bonds are side-on overlap. Like sides of a pi, side on pi bonds. I don't know. Anyways. All right. Any questions? Okay. Good. All right. We get into polarity. Oh. Okay, so polarity means that one atom has a stronger pull on the electrons than the other atom. Differences in electronegativities to determine polarity. So the value you should be familiar with. I remember the middle one, and then anything below meets one requirement, and anything above meets the other requirement, to make it simple. Okay, so the nonpolar ones are formed when the difference in electronegativity is between 0 and 0.4, and we have equal sharing of electrons. So the most common example is when you have two equal atoms. So in the case of Cl-Cl, they have the same electronegativity, so they're going to pull those electrons equally, and so we're going to have a nonpolar or a pure covalent bond. And then hydrocarbons, CH, are considered nonpolar or pure covalent. Okay. For polar bond, they're formed when the difference in electronegativity is 0.5 to 1.9. And we have an unequal sharing of electrons. So this is the case, for example, for HCl or HF or HBr. They're going to be polar because that chlorine is pulling those electrons more strongly than hydrogen. So the difference in electronegativity in this case is 0.9. Oh, and you may see it as, I think it's written like that, difference in electronegativity. For ionic bonds, it's formed when activity difference is greater than 1.9. So in this case, we don't even have, so if you think about it, in ionic bonds, we don't even have sharing of electrons, we have transfer of electrons. Like it's the case for sodium chloride. So remember how you would see it would be at electron 2, 4, 6, 2, 4, 6, and then 7. So chlorine is missing 1 electron, and so that's when we see that that electron travels and fills the outer shell for chloride. So we have something like 2, 4, 6, 8, negative. Does that make sense? Yeah. All right. Can I switch? All right. So 2 conditions must be true for a molecule to be polar. There must be at least 1 polar bond or 1 lone pair of electrons present. And the polar bonds, if there are more than 1 in lone pairs, must be arranged so that their dipole moments do not cancel each other. So in this case, we have that they have dipoles. There's a dipole in this bond because fluorine is more electronegative, so it's going to have a partial charge of negative, and then carbon is going to have a partial positive charge, since those electrons are traveling from carbon to fluorine. But in the case of molecules, we can have molecules that have polar bonds but are non-polar, like it's the case for CO2. So I always use as examples CO2 and H2O. So I think they represent like a good difference between these two conditions. Okay. All right. And then no, that's worse. There you go. All right. So you know that the structure for CO2 looks like this. 2, 4, 6, 8. 2, 4, 6, 8, right? And then for H2O, we have the O in here, and the H, and the H. And we have 2, 4, 6, 8. Okay. So let's review CO2 for a bit. Okay. So that, like, each individual bond towards the oxygen. Oh my god. Let me try to fix it. No. Okay. No. Oh god. Alright, I think I'll leave it there. Okay, so you know that these bonds are polar. So we see that carbon in there will have a partial positive charge because it's losing those electrons to oxygen, which gains a partial negative charge. I don't know if you guys can see. Probably not. Okay. Oh my god. Okay, there we go. But it's the same case as for the other side. So this oxygen atom is also going to have a partial negative charge. So in here we run into the situation where, despite the fact that the CO bond is polar, the whole molecule is nonpolar because the dipoles cancel. So here we have a net dipole of 0. And I emphasize CO2 because I got this wrong on one of my tests, so I don't want you guys to make the same mistake. Yes. All right. Now we see the case of water. Same scenario. Those electrons are traveling from the hydrogen to the oxygen and hydrogen to oxygen. So hydrogen has a partial positive charge, partial positive charge. And then oxygen acquires a partial negative charge. Since they don't cancel because of the geometry of the molecule, they actually add up, those two vectors actually add up to a net dipole that goes straight through oxygen. So we say that the net dipole for this molecule is not equal to 0. So as you can see from these two examples, you can have polar bonds and yet have a molecule that's nonpolar. So it's really easy to see when you're looking at your handout. Because remember, if you draw your Lewis structure and it falls to have like anything on this first column, it's going to be nonpolar. So that's why drawing your proper shape is important. It's going to determine that. So all this, it's nonpolar. Okay. And not because you have lone pairs of electrons, your molecule is going to be polar automatically. Remember that Dr. Patino, if you're in Dr. Patino's class, he emphasized that this, despite the fact that it has 3 lone pairs, it's considered nonpolar because this will cancel with this. So remember that this will be nonpolar. Same as the scenario with the square planar, since this cancels with this and this cancels with this. If we look back at the exercises we did, we see that BF3, so it's non-polar because they cancel out, like the orientation. It's like these two add up and are canceled by this one. It falls on the first column. For IF4, it's a seesaw, and there's no cancellation of this one. So we see that this molecule will be polar. So there's no complete cancellation of the dipoles. And then for the carbonate ion, it will be non-polar as well since it falls on that first column. So does that make sense to everyone? Yes? Okay. All right. So one student said, like, if you can fold it like a taco, like if there's symmetry. So symmetry is a keyword for polarity of molecules. Symmetry. Key. So if there's symmetry, even if you have polar bonds, your molecule will be nonpolar, since the dipoles will cancel each other. All right, we get into hybridization. So in order to determine that, count up the sigma bonds and lone pair of electrons, determine the principal energy level of atoms' valence electrons, take s orbital to hybridize, and take as many p orbitals and d orbitals, if applicable, for the same number of orbitals hybridized as sigma bonds and lone pairs. So all that is fancy words for simply counting the bonds and the lone pairs, like your electron group, total number of electron groups that you have in the molecule. So in this case, so remember that we only have one s orbital, 3 p orbitals, and 5 d orbitals. Right, so we just count up. So we have one bond, it's s, we need one s orbital, and then the other one will be a p orbital, because we ran out of s orbitals. So the hybridization for that would be sp. If we move on to the second row, we're going to have s, p1, p2. So sp2 for hybridization. And notice that you count the electron groups, so s, p1, p2. So remember to count those lone pairs. Oh, and also remember that when we're doing this, you don't count like double bonds as 2, you count it as just like the electron region. So don't forget about that. So in here we have s, p1, p2, p3, s, p1, p2, p3, and so on. So hybridization is sp3. And here we have s, p1, p2, p3, and we ran out of p orbitals, so the next one would be d. So sp3d hybridization. S, p1, p2, p3, d1. Same thing. And then lastly, for our sixth row, s, p1, p2, p3, d1, d2. So sp3d2 hybridization. Does that make sense? Yeah, okay. Good. So, do you guys want me to draw like why this happens, like the hybridization? No? I'll take that as a no. Okay. All right. Okay, so we kind of like reviewed this when we were drawing the structures. So valence shell, electron pair repulsion theory, VSEPR, I just call it VSEPR. Regions of high electron density, electron pairs around the central atom are arranged as far apart as possible to minimize repulsions. and the lone pairs of electrons require more volume than shared pairs. So lone pair to lone pair is the strongest repulsion, lone pair to bonding pairs, intermediate repulsion, and bond pair to bond pair is the weakest repulsion. So that's why if you have lone pairs, then the angle between if you have lone pairs of electrons, the angle between those atoms is going to be decreased, except for, it says it on your sheet. Well, I don't think you're going to have the backside to this, but. So when lone pairs are present, bond angles are slightly less than those given, except in the cases for linear, where we have 180 degrees and square planar. So when only two atoms are present, it is inappropriate to speak of bond angles. So you only speak of bond angles if you have more than two, and so your angles for square planar are still going to be 90 here, and then 180 here, despite of having lone pairs. This was me trying to find a table that resembled the one you get, but then I remember I had the handout, so. Okay, and I added this one because I think it really emphasizes that the fact that you have lone pairs changes your molecular geometry, but not your electronic geometry. So don't forget that. They like, in multiple choice questions, they like to switch them up to see if you really know the material. So don't fall for that. All right. So I like that this brings all together. So quick notes that I saw from students taking the quizzes. Remember that if you have a CH3N, you have to expand that. You have to actually write CH3 so that you choose the correct number of sigma bonds or double bonds or like pi bonds, depending on the case. I saw like many miss that, so don't forget that. And then the other thing is that they may give you the structure like this, but not put all the lone pairs that you would need to fill up the octet. So 2, 4, it's missing 4 more electrons in that case. So that if you need to write that down to get the appropriate hybridization for each element, in case that they don't have them. So again, S, P1, P2, P3, S, P1, P2, S, P1, P2, same. And remember, you don't count, you only count the double bonds once. S, P1, P2, P3, so sp3, sp2, and then 2, 4, 6, so this nitrogen is missing a lone pair. So S, P1, P2, P3. So remember that we have 1 sigma bond in the single bonds and then 1 sigma bond in those double bonds. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So I counted 25. Just count them yourself. Did everyone get 25? I don't know if you counted them. But. Okay. And then for pi bonds, we have 1, 2, 3, 4. 4 pi bonds. Also, another thing to keep in mind is, despite the fact that you see this bond like this and you think, oh, maybe that looks like a 120, it goes along with the hybridization. So if it's sp3, remember that your hybridization, your angle will be 109.5, or like less than in that case since it has lone pairs. So don't get tricked by seeing like maybe something has like a right angle. No, go by the angle that follows the hybridization. So in the case of sp2, the hybridization, the angle would be 120. You guys have any questions? No. Okay. All right. So we get into the bond order and molecular orbital theory. So you have to be able to fill out an energy level diagram. So remember, when you have less than 14 electrons, you have to choose this one, and then when you have more than 14 electrons, you use this one. And the difference is that they both start with sigma and pi, but in this scenario, for less than 14, they have sigma and pi, and this one is pi sigma. So sigma pi, pi sigma, sigma pi, sigma pi. There was a mnemonic for it, but I don't remember it. If I see it, I'll post it on my WordPress site so you guys can have it. So I have handouts. I have a couple of copies if you want to take one at the end. So I'll go ahead and do the molecular orbital diagram for C2 minus 2. Oh, and I didn't go over this. So bonding orders, number of electrons in bonding molecular orbitals minus the number of electrons in anti-bonding molecular orbitals divided by 2. So we have C2 minus 2. So remember, in here we're using total number of electrons, not just valence. Don't get confused. So carbon has 6 electrons. So times 2 is 12, plus the 2 that we added is 14. So we're okay using this right now. So we fill them up. 2, 4, 6, 2, 4, 6, 8, 9. So the same rules with filling apply. So you're supposed to put 1 electron in the first orbital and then the other one in the following one. Do not fill one and then the other one, because that's violating Hund's rule. 2, 4, 6, 8, 9, 10, 11, 12, 13, 14. All right, so that's what I got. So from that, we can see that this compound is diamagnetic. So remember the difference. So paramagnetic, unpaired electrons. So in here, all of them are paired. So diamagnetic. And this is important because paramagnetic, since they have unpaired electrons, they'll be attracted to a magnet. Para, I remember that's 2, so attracted to the magnet. So this compound is diamagnetic. And then for the bond order, we know is bonding minus anti-bonding divided by 2. And we have, so remember the ones that are anti-bonding have the asterisks on them. They're higher energy than the ones that are bonding. So bonding, we have 2, 4, 6, 8, 10. And anti-bonding, we have 2, 4, just 4. Divided by 2, so that gives us 10 minus 4 is 6, divided by 2 is 3. So the bond order for this compound is 3. Then what else? The spin will be 0, since all the electrons are paired, and then plus 1/2 minus 1/2 be equal to 0. I think that's all. Yeah. Does anyone have any questions? No? Okay. So the significance of this, remember if your bond order is equal to 0, the compound is very unlikely to exist. Compound is unlikely to exist. If you guys can see that. No. Well, okay, I don't know. Oh, there we go. Okay, if your bond order is 1, typically it corresponds to a single bond. If it's 2, double bond, and then 3, triple bond. Alright, I think that's all I remember for that. Okay, so we're almost done, guys. Getting into gases, so our last portion of the class. So remember that our pressure always has to be in ATM. We also have other standard units like the millimeters of mercury and torr, but remember that you have to know these conversion factors to be able to change it to ATM, because most of our equations require ATM. So the one that's missing here is the kilopascals one. So remember you have to know those 3. So 760 millimeters of mercury and 760 torr are all equal to 1 ATM. That's an ugly M. Okay, M. There we go. All right, zoom out a little. Okay, so temperature, remember we use Kelvin. So in order to convert from Celsius to Kelvin, we add 273.15. So units are like super important for chapter 5 problems, because if you're using the wrong unit, you're going to get the wrong answer, unfortunately. So make sure you're using the appropriate units. Density, mass over volume, and then remember that you can find mass from using PV equals nRT to find moles and then converting. So I'm gonna go ahead and show that to you guys. All right, so remember our ideal gas law formula is PV equals nRT. So from there you can actually find mass, molar mass, and density. So make sure you know how to find those things using that equation, because you'll maybe have a problem like that. So, and I'm going to show you how to find these things, and it's not difficult. It's just algebra. So remember, if you're going to look for a weight, a molecular molar mass for an atom, you say, okay, the molar mass of oxygen or like carbon is 12 grams per mole, right? We can say, so the unit for this will be M, and then mole, we can represent it as N, right? So that would give us M equals little m over N. So if we rearrange that, our N is going to be equal to little m over big M. The good part about this is that we can plug in this into here if we need it. So PV equals nRT, PV equals little m over big M times RT. So that works if you're looking for mass or molar mass. If you're looking for density, you have to do a little rearrangement. Remember, density is equal to mass over volume. So we need to have volume underneath this mass. So PV times M divided by RT will be equal to M, right? But we need mass over volume, so we move this V to the bottom over here. P times M over RT equals M over V, which is density. So you should be able to, you should be familiarized with how to find this. If you want to remember the formula, of course not advice, because if you forget it, then yeah. But someone said, okay, so density equals to PM, like nighttime, so PM over RT, retweet, so nighttime over retweet equals density. I don't know if mnemonics help you. Okay. There you go. So remember, standard temperature and pressure. Temperature is 273 Kelvin, pressure is 1 atm, and volume always has to be in liters. Liters, not milliliters, liters, so it cancels out. So we have some laws. Boyle's law says that pressure of gas is inversely proportional to its volume. PV equals PV, so P1 V1 equals P2 V2. Think about it when you breathe. When you breathe in, your chest expands, so more volume at a decreased pressure. And if you breathe out, you're putting pressure into your chest to make that air exit, that carbon dioxide exit, and so your volume is decreasing. So they're inversely proportional. For Charles' law, volume is directly proportional to temperature. So like those hot air balloons, they have hot air in them. They increase the temperature so that the volume increases, and you can have those hot air balloons. I remember as like Charles, like C for cooking, temperature. So this deals with temperature. I don't know if that helps you. Avogadro's, so volume is directly proportional to the number of particles. V1 over N1 equals V2 over N2. In standard conditions, they're 1 atm, 273.15 Kelvin. Yeah. And then the mole fraction, remember that, I don't know if it says it here, but remember that Dalton's law of partial pressure tells us that the partial pressure of all gases equal to the total pressure. And so we can find the partial pressure of gas A, for example, by using the mole fraction. So how many moles of A are in the total mixture times the total pressure. So that one's very important to solve problems. All right, and you can use water displacement to collect the gas. You can subtract the partial pressure of water vapor from the total pressure to find collected gas pressure. We also have molecular velocities of gases. So your average speed is equal to the square root of 3 RT over molar mass. So remember, this means that lighter particles will travel faster than heavier molecules. And so that makes sense because molar mass is at the bottom of these equations. So if this increases, this decreases. And so something will travel faster if there's higher temperature. So higher temperature, higher average velocity of the gas. So things to keep in mind. Remember though that kinetic energy is directly proportional to temperature. And so all molecules would have the same, all gas molecules would have the same kinetic energy at the same temperature even if they have different masses. So there's a difference between kinetic energy and molecular mass. So don't confuse those. Real gases. In real life, intermolecular interactions occur and volume of particles actually has an impact. So we have to use van der Waals constants to account for these factors. So ideal gases, we use this equation, right? But then for real gases, we use this readjusted equation. And this happens when we are at, let me not give you wrong information. Yeah, high pressures and low temperatures. High pressures over 1 atm. Ooh. 1 atm, low temperature. Less than 0. All right. And so this accounts for intermolecular forces at low temps, and this accounts for volume of gas particles at high pressure. All right, diffusion and effusion, it's a very important concept, but it's easier to understand. So diffusion is just traveling according to the gradient. So greater concentration to lower concentration until equilibrium is reached. Whereas effusion, that traveling happens through a small pinhole, like it's the case for like birthday balloons or helium balloons. Yeah. All right. All right. So getting into the gas problems, I'm gonna run through them quickly because we're almost out of time. So 15.1 grams of C4H10, 1 mole. So they're asking us about the volume of O2 required to react with 15.1 grams of that. So all of these, so this Celsius and this ATM is related to O2. So we can use 15.1 and the equation to convert to, like we can use the mole fractions to convert to that. So 15.1 grams, 2 moles, and then moles, there's 2 moles of C4H10 per 13 moles of O2. And that gave me 1.69 mole of O2. And so when plugged into our PV equals nRT, our ATM was fine, our pressure was fine like it was. We're looking for volume. Moles, we plugged in what we just found for O2, 1.69 mole O2. Our gas constant, 0.0821. And then our temperature was converted from Celsius to Kelvin, and that was 290.9 Kelvin. And so the volume we received was 41.227 liters. Yeah. Sorry about that. There you go. All right. You guys ready? No. Alrighty. Mm. Alright. Okay. You got it? Yeah, okay. Alright. So density, so really easy now that you know how to find that. So density would be equal to nighttime or retweet. So density would be equal to the pressure, 0.693 atm, times the molecular mass of krypton, which is 83.80 grams per mole, divided by 0.0821, and then temperature is 308 Kelvin. All right, so the value I received was 230 grams per liter. And then this number 3 is very similar to the one you found on your quiz last week. I think it might be the same one actually. I don't know. All right. So a sample of oxygen was collected by displacement of water at 25 degrees Celsius. The atmospheric pressure was 700 torr. What is the mole fraction of O2? Vapor pressure of H2O is 24 torr at 25 degrees Celsius. So remember that we can find the total pressure. Well, in this case, you don't need that. Never mind. All right. So they're asking for the mole fraction. So remember, we can find, for example, gas A, mole fraction of A times PT, right? And they're looking for the mole fraction of oxygen, so partial pressure of oxygen, mole fraction of oxygen times PT. Oh, not PT in this case, P H2O, since it's water displacement. And so okay, so remember PT equals PH2O plus PO2, and so we have 700 equals 24 plus PO2, 700 minus 24 equals PO2, so PO2 is equal to 676 torr. So we found the partial pressure of oxygen, and so we can now find the mole fraction. So PXO2 equals 676 torr over 700 torr equals 0.966. So remember, your mole fraction should not have any units. Just leave this one as PT. So XO would be equal to PO, like partial pressure of oxygen, over PT. So 676 over 700, which was the atmospheric pressure. And that was it. Good luck on your test, guys. You got this. I'm sorry?
The packets.
Oh, like the molecular orbital thing? Oh yeah, sorry. Really quickly before you leave, I have to give you the surveys. Thank you for reminding me. All right. Yeah, go ahead. All right. There you go. There you go.
Do you have an extra copy of the packet?
Of what packet?
That sheet? The one we just went over?
No. There you go. No.